I am Sumanth Udupa. I am going to give a brief seminar on solutions to common parallel programming problems using multiple threads. These are all the topics I am going to cover now. We already know that if we use the threads in executing the program, then it definitely reduces the program execution time. But this is true only up to the extent. There are many performance problems arise by increasing the number of threads. Actually, we are going to distribute the work among the number of threads that we have created. If too many threads means each thread will get only a small amount of work. So here there is an overhead of starting and terminating the threads. It will take too much time to start and terminate it all. And also the software threads fight for the hardware resources. When the number of threads exceed the total number of hardware threads, then OS will use the round robin scheduling. Here, each software thread gets only time slice to execute on the hardware thread. After the slice period is over, then opportunity should be given to the next thread in the queue. Hence, the currently running thread is preempted by the scheduler after saving the threads constant. This time slicing technique somehow allows software threads to progress by giving opportunity to all the threads. But somehow there are also overhead in this scheme. First is saving and restoring the thread register state. Here, once the time slice is over, then it has to store the hardware thread register value in order to continue the execution of the thread in next time slice. So, time required for the storing and restoring the thread is much overhead. The second overhead is saving and restoring the thread's cache. We all know about the cache, which is 100 times faster than the main memory. Accesses that hit in the cache not only much faster, but also it don't need the memory bus at all. Caches are fine, but what the problem with the cache is, it is finite. So when the cache is full, the processor must have to replace the data in the cache in order to make a room for the incoming data. So when the time slice is over, it will give opportunity to other thread. So if the cache is full means it has to evict the data of the other thread. So it will going to hurt the performance. So another overhead is crashing virtual memory. Yeah, virtual memory is resides on the disk, and the frequently used portion of it is kept in the real memory. It is similar to cache. The least recently used data in the real memory is replaced when we need a room for the incoming data. So each software thread requires virtual memory for its stack and other private data structure. So as with the caches, time slicing causes threads to fight each other for real memory, and it will hurt the performance. This cache and virtual memory issues is mainly because of the limited resources that will be um, sharing among the too many software threads. Uh, One problem arises here is which is known as convoying, in which software threads pile up waiting to acquire a lock. Consider a situation in which a thread slice has been expired, but it has locked one of the critical section. Then the time slice is given to another thread. If it wants to acquire a lock on that critical section means it has to wait until the lock thread wake up and and do something on the data in the critical section and unlock it. So it will be a major problem here. There are in order to building a efficient task queues, there we can use the three ways that shown here. First is open empty handling. in which we allow the OpenMP to do its work. Mm, Here, as long as the programmer does not request a particular number of threads means OpenMP implementation will use the optimal number of software threads. And the second one is use of the thread pools. Uh, we already know which thread pool is a construct that is used to maintain a set of long-lived software threads, and it actually eliminate the overhead of initializing process of the threads for short-lived tasks. uh, a thread pool which is a collection of tasks, so which are serviced by the software threads in the pool. When each software finishes a task, means it will come back to the thread pool and waiting for the another task. In this scheme, we don't require the initialization process for the threads. We can use the threads in the thread pool, it will eradicate the initialization process. And the third one is work stealing. In this, each thread has its own private collection of tasks. So when the thread run out of its task means it steal the task from the other threads. So two benefits from this is cache usage and load balancing. Cache usage means it's going to work on its own private data, means it will efficiently use the data in the cache. Load balancing here means other threads going to steal the work mm, from the from the threads that is having too much of work. That is race condition. Data races, which is due to the unsynchronized access to shared memory, which means there is a shared memory. There is no synchronization between the threads. So whenever the thread wants means it can actually use those resources. There is no synchronization. So they are competing for the this shared memory, and they can update the memory whenever they want. From this, what will happen is the program results, which is dependent non-deterministically on the relative timing between the two or more threads. Is uh, Somehow races can also be hidden by the um, language syntax. Actually, these race conditions can be handled by locking. This races is actually due to the unsynchronized access. So we can make it synchronized by using a lock to the critical section. So in order a thread wants to use the critical section means it has to lock the critical section and has to use. If a thread lock the critical section means other thread cannot use that critical section. So there will be a synchronization among the threads. And then deadlock, yeah, we all know about the deadlock. So which is uh, yeah, we know race condition can be handled through locking, but this locking is the that is responsible for the deadlock. Consider two threads, one thread, two threads and two resources are there. One thread is handling a first resource and wants to get a second resource, and another thread is there which has acquired the second resource and waiting for the first resource. So there will be a cycle among these threads. So thread 1 is waiting for second resource, thread 2 is waiting for first resource. So eventually they are not going to give up the resources, so there will be a cycle among them, which is known as deadlock. A live lock means which is as same as deadlock, but what happens here is uh, continuously conflict with each other and back up. Here, if uh, multiple if you consider if the thread wants multiple locks means it's going to check it's going to acquire the lock in order by order. In live lock, let's consider there are two threads. These requires two mm, resources. First thread is holding on resource 1 and waiting for the resource second, and the second thread is holding on resource 2 and waiting for resource 1. So it cannot acquire because of the deadlock. So they are going to back off and wait for a random number of time. So if the random number of time is same means no thread makes any progress. This cycle will repeats. This is known as live lock. This shows how the race among the threads will affect the program performance. We can see the original code for thread 1 and thread 2. In first case, after the thread 1 executing the first line, the thread 2 interleave with the uh, first thread. So output x is 1. In the second the interleaving is in a different fashion. So for thread 1 x output is 1 and for thread 2 x is 2. In the third case, we can see the output is different through when compared to the other two cases. Here x is the shared memory. So this race condition will affect the program output. This shows the race conditions hiding behind language syntax. Yeah, we already write in the code like x plus 1, x plus is equal to 1. Yeah, what the compiler will do, it expands means first it will store the x value in the temp and then update the temp value and store it back. So interleaving can be happen in these sequences. So in first case, compiler may expand that plus is equal to 1 into separate read and write of x. So interleaving can be happened there. And in second case, these I and j subscript may be equal. So both the threads are going to write to the same memory. And in third case, p and q may be point to the same location. So the in first thread may increase the value by 1 and the second thread will update the value to 2. This can be interleaved. And in the next one, uh, these functions. So it foo may contain the hidden shared variable that's going to update the shared variable through the arguments that we have specified. And then last one is even at the instruction level can also be interleaving can be possible. Here what the hardware will do is which expands the update of EDI into separate reads and writes. Yeah, I already told that the race condition is because of the unsynchronized access. But race can also be happened by using the synchronized access. But this synchronization is very two level. Let's consider an example. There is a list which contains a key. So every thread wants to update the list by adding the key means mm, key. So we can see the program there. Here first thread will check whether the key that is going to update into the list is there in the list or not. If the key is not in the list means it can update the key. So this here after first line the interleaving can be possible. You can consider two threads have wants to update the same key. they at the same time they are going to execute the first line, and they think that the key is not in the list. So what they will do is they will update it at the same time. So it will contain the two list will contain the two keys. So race condition will affect the program output like this also. Mm. And then we can uh, the, eliminate this race condition by using the logs. uh, this is the very two level example. So uh, we can use a lock on this list, so allow only a single thread to execute the list. But this logs at the two level is just a waste of time. This this two low level components are held by the higher components that are that should be locked in order to execute. So mm, this logs at the low level is just waste of time. This shows the figure how the deadlock will be caused. Here thread 1 holding lock on the a resource A, and thread 2 holding lock on the resource B, and they are waiting for the each other's resource. So these two cannot be processed because uh, there is a law there is a cycle uh, there is a cycle form between them. Yeah. These are the four conditions for a deadlock. Deadlock, deadlock. In order to occur deadlock, these four conditions should have to satisfy. Access to each resources is exclusive. Yeah. And then second point is thread. Thread is allowed to hold one resource requesting another resource. Third point is no thread is willing to give up a resource that it has acquired. And the last one is there is a cycle of threads trying to acquire resources where each resource is held by one thread and requested by another. So last point is as same as the figure that previously I explained. Yeah, we can prevent this deadlock. How we can prevent the deadlock? We can prevent the deadlock by ordering the lock acquisition. Means we can order the lock. Here in this ordering, we are actually going to define which locks should have to uh, come first, and the next log. The thread has to follow this order only. Means if if the order is x y z, means each thread has to follow this order only. Has to first acquire the log x and y and z like this. Here these x and y, here in this figure we can see that x and y are the pointers that are point to some of the containers or any data. If the thread wants to acquire this log, it has to follow this order only. If x is less than y, means it has to acquire x, and then it has to acquire y. If x is not less than y, means it has to acquire log on the y first, and then has to acquire log on the x. Try and back of logic. Here this is for multiple logs. Yeah. Consider there are two threads, and they are going to acquire logs on two resources A and B. Yeah. First, try and back of logic says that first thread, it is holding the lock on resource A and waiting for the second resource B, and the thread 2, which is holding the lock on resource B and waiting for the resource A. So thread if the thread can't uh, acquire the lock means they are going to back off. So they will release the lock and wait for a random amount of time, and then again it will come after a random amount of time to acquire the lock. So it can assure that waiting for random amount of time may uh, allow it to acquire lock on whatever the locks that it requires. Yeah, let's come to the heavily contended locks. This is caused by the race condition. It occurs when threads try to acquire a lock mm, faster than the rate at which a thread can execute the corresponding critical section. So, a thread going to acquire a lock, it's going to execute on the critical section. If other threads wants to acquire the locks, they so many threads comes at the rate that is faster than the thread that is executing means there is a queue behind the locks, so waiting to acquire the locks. This is known as heavily contended locks. This is known as uh, this is all this behavior as referred to as convoying. Yeah, I have already explained what the convoying is. This we can this actually degrade the program performance. Yeah, in the priority inversion scenario, I will explain what the priority inversion is. Yeah, actually, threads are having the priorities. Yeah, which thread has to execute first, and then which has to execute second, like that. Highest priority thread will be executed first. Yeah, consider there is a lowest priority thread that is executing means which has acquired a lock at the time highest priority thread came. What it will do is thread it lowest priority thread will be preempted and gives opportunity to highest priority thread. If highest priority thread wants to mm, acquire a lock lock on the critical section that has been acquired by mm, lowest priority queue means it has to wait. So what it will do is it will allow lowest priority thread to execute. Or if the medium priority thread comes means it will preempt the lowest priority thread and it's going to execute. So medium priority thread will have the here in this situation medium priority thread will execute mm, within the with the highest privilege. So this lowest priority and highest priority will have to wait for this medium priority thread. So this condition is known as priority inversion. This here they are giving the examples of the car and the driver. Car and the driver. Here car means the hardware threads and the driver means the software threads. There is another alternative to this priority inversion is priority ceiling, in which we can consider to assign it to a mutex. This ceiling is the highest priority of any thread that is expected to hold the mutex. When a thread acquires the mutex, its priority is immediately bumped to the ceiling value for the duration that it holds the mutex. The priority ceiling scheme is eager to bump up the thread's priority. Uh, Solutions for this heavily contended blocks. In this, uh, we can consider an example in which there is a hash table is there. If only one thread can acquire a lock on thread means there is a heavily contended lock means many threads will be waiting to get that lock. So what we can do is we can divide the hash table into a sub into subtables, and we can assign the logs for each of these subtables. So any thread uh, that wants to hold on the log means it will execute a hash function, so it can direct to any of these subtables. So it can hold the lock on these subtables, so contention will be less as compared to the previous case. And hash table with fine grained locking. Yeah. Actually, the what here hash tables are commonly implemented as array of buckets, where each bucket holds keys that hash to the same array element. In fine grained locking, there might be a lock on each bucket. Uh, this way, multiple threads can concurrently access different buckets in parallel. So uh, this this in this case we can't handle the uh, handle the dynamic resizing of this hash table. So what we can see in this table, array descriptor, which is holding the array size, array pointer, and the read writer mutex, and the array of buckets. We can see that mutex is protecting each bucket. In order here a thread wants to um, use the list means hash table means it has to acquire two logs, one on the array descriptor, that is reader or writer mutex, and then on the plain mutex which is on the bucket. So if a thread only wants to read means it can acquire reader log log on the array descriptor. So many threads can acquire reader logs on the array descriptor, but only one thread can acquire the writer log. Yeah, yeah. This non-blocking algorithm. Uh, we already know this how locking may cause the deadlock problem and how to we use non-blocking algorithms to resolve the locking problems. Uh, so this is known as non-blocking. This stopping one thread that does not prevent rest of the system from making progress. Non-blocking non-blocking algorithm guarantees first is obstruction freedom. Thread makes progress as long as no contention. Here, leave lock is possible, which uses exponential backup to avoid it. Okay. The second one is lock freedom. System as a whole, here system as a whole makes progress. In wait freedom, as the name indicates, every thread makes progress even when faced with contention, particularly which is particularly difficult to achieve. Yeah, this shows the atomic operations and race conditions. Yeah, in non-blocking algorithms we are not going to use the log. So how can we synchronize between the log? There is a program there. Here it going to uh, decrement the reference count. So here in this I already shown here the in the first case it first thread what will do is it going to decrement the first, and then it will check the reference count. If reference it's sorry, it's wrong there. This p of reference code is double equal to 0 has to be there. So if this reference code is 0, it can delete it. So what here after the execution of the first line, another thread may also decrement before the execution of if statement by the thread 1. So we have how to solve this is we have to make this as an atomic operation, means decrementation and the comparison of the reference code should be in the same line. So second code is the best one. So it will going to decrement and this reference and check whether it is equal to 0 in the same statement. Yeah. And second shows lock and lockless code for the fetch and move. Here Here, first one shows the locked version and the second one shows the unlocked version. Not unlocked, is shows the non-blocking version. Here, it's going to acquire the lock and doing some of the operation on this shared variable x and release the lock. And here, mm, in the non-blocking, we don't need a lock. So what it will store? It will store the x value in the variable x volt and going to mm, make some of the operation on the x value and store it in the x new, and it's going to check in the interlocked compare exchange. What it will do is it will check whether the x word and the x are same. If those are same, the another thread is not change the value of the x. So we can mm, conclude it as this is having the synchronized access. But there is one problem here, ABA problem. We can see there is a time interval between when the thread executes x volt is equal to x and when the thread executes that interlocked compare exchange. During this interval, other processors might perform other fetch and op operation. For example, suppose the initial value read is a, an interleaving sequence of fetch and op operation by other processor might change x to b and then back to a. When the original thread executes this interlocked compare exchange, it will be as if the other processor's action never happened. As long as the order in which OP is executed does not matter, there is no problem. The net result is the same as if the fetch and operation were reordered such that the intervening sequence happens before the first read. This is the ABA problem. Then thread save functions. In thread save functions, you can say in the previous example, the foo example, that is having this hidden share state. Uh, so routine like that foo that updates the unprotected hidden share state, which is a poor programming practice. So we have to design the routines in such a way that it should be thread safe. Means concurrent access should not corrupt the data in the share state. Yeah. We can see in the figure there are the users, clients or users. See that they have the separate string object for them, but actual implementation is these objects they point to a shared object. They you can see here they point to a shared object that is having the shared data. So the reference count which tracks now how the number of objects that point to this shared object. So we have to design the this in such a way that concurrent access to these objects by the threads will not corrupt the shared data. The implementer should ensure the thread safety of hidden share state. Next is memory issues. Now, we know that these microprocessors have grown much faster in speed than memory. A single microprocessor core can execute hundreds of operations in the time it takes to read or write a value in main memory. Program so programs now are often limited by the memory bottleneck, which means if the program accesses the cache memory means it will runs faster. If it depends wholly on the real memory and swapping is required means here memory issue is the great problem. So these are the memory issues that I am going to discuss now. Bandwidth. Yeah, we all know what the bandwidth is. Bandwidth means it's the transformation of data from uh, memory to the processors required. It requires some of the channels and all. That is bandwidth. Bandwidth is higher means we can transfer the data much faster. So what we can do is to conserve bandwidth, we can pack the data more tightly that moves frequently between the cores or the data transfer between the core and the memory. We can pack it so it eliminates the frequent sending of data by bit or part by part. So we can see here in there are two structuring can be done. First is loose structuring, tight structuring. Here loose structuring, the packing of data is done in the decreasing order means it first short is assigned and then int, then cat, then full stop. And in tight, there is they have packed the data in increasing order of the memory it consumes. Means post or p means it will consume more memory and then int, then short, then cat. This tight packing of data this minimize the extra padding that the compiler must insert to maintain alignment requirement. So this tight packing of data to send to the cores or between the cores or between memory and the cores has to be preferred as, as compared to the loose ones. Here the tight packing will extensively conserve the bandwidth when it compared to loose packing. Yeah. Then next is working in the cache. Here, in the previous we have discussed how to conserve the bandwidth. We can allow cache to store the data without it to um, access from the main memory. Means if the cache has the data means we don't need to bring the data from from memory to the cache processor to every place. So we think cache is the main point here. So moving data that is less frequently is more useful than packing. So um, so we have to utilize the cache in such a way that the program will almost execute by using the data within the cache. So in order to use the cache in the efficient way, we have to write the programs in cache optimization form. So this plot explains us the white mark that is cache friendly and black mark which is cache unfriendly seeds. This shows the performance difference, and we can see on this log spot the cache friendly code has a fairly straight performance plot, while the cache unfriendly version when you can see when n reaches to approximately 10 to the power of 6 this plot is running which steps up one straight line when we compare to the cache friendly C. So we can see the time to execute the program or performance is much higher when we compare to the cache friendly um, uh, with respect to the cache unfriendly seal. So we have to make utilize the cache data more and more, than have to uh, bring the data from the main memory using the bandwidth. Memory. Now we are using multiple cores. So memory access is not only between the core and the main memory, but there should be an interaction between the cores also. So two types of dependencies, that is the dependencies are there. Read write dependency. Here a core writes a cache line, and then different cores read it. In write write dependency, a core writes a cache line, and then a different core writes it. That's it. Yeah. What if multiple cores only read a cache line means, it don't write means, then we don't need the bandwidth. So bandwidth is not consumed here. So in order to minimize the memory bus traffic and minimize core interaction, we should have to minimize the shared location. Yeah, the shared location causes the memory congestion by acquiring locks and allowing other threads to wait. So it's the same pattern that tend to reduce the lock congestion, also tend to reduce the memory traffic, because it is the shared state that requires the locks and generates the congestion, letting each thread work on its own local copy of the data, and merging the data after all threads are done can be a very effective strategy. The processors that interchange or interact is through the cache line. So if two separate caches can share a cache line when they both need to read it. But if the line is written in one cache and read in another, uh, what we can do is, it should be shipped between the caches. If even if the locations of interest are disjoint. So here in this case, you can see the figure. It illustrates that it is like a ping pong game. There are We can consider there are two threads which are each running on a different core. Each thread increments a different location belonging to the same cache line. But because the locations belong to the same cache line, the cores must pass this sector back and forth across the memory bus. This is false sharing. This is just shows the performance impact of the false steering. This is just the generalization of the figure, so figure that we have seen in the previous slide. That's it. There are two types in memory consistency. First is sequential consistency, and then relaxed consistency. At any given instant in time in a sequential program, memory has a well-defined state. It is known as sequential consistency. Now we can see in parallel programs, it all depends upon the viewpoint. Two writes to memory by a hardware thread may be seen in a different order by another thread. So those two threads, we can't expect those two threads within the see in the same order. They can see in the different order here, because when the hardware thread writes to memory, the written data that goes through like buffers, and then caches, and then main memory. Uh, so for text to go to buffers, caches. Uh, so it will go to these ones before going to main memory. So you can't expect another thread to see the same data. So the same data means memory consistency. Along this path, the write may read the main memory. We can't expect when the main memory write will reach to the main memory. It will reach for as fast as possible, or it will reach reach um, in a later way. We can apply this to read also. So we have a thread has to read means it first has to read from the cache, and then from the main memory, like that. But the processor, what it will do is, it does not have to guarantee that other processors see those reads and writes in the original order. This is known as the relaxed consistency. Yeah, this shows the current IA32 architecture. It will demonstrate the key sequence in Baker's algorithm. IA32, which approximates the sequential consistency. Okay. Then there are two rules in programming in IA32. The first is relaxation, which is for performance purpose, and the second is strictness. Mm. And then as I have told, this figure for this one, A represents the key sequence in Decker's algorithm. We can see the two variables x and y. There are initially zero. Two threads which writes x and reads y. The first thread do this, which writes x and then reads y. What the second thread will do is, first it writes the y and then reads x. Uh, on a sequentially consistent machine, no matter how the reads and writes are interval, no more than one of the threads reads as zero. The thread reading the zero is the one that allowed into the exclusion region. So on the IA32 and just about every other modern processor, both threads might read zero. So B, which behaves as the return like purpose. The C, the seventh, this one, Cth one, that shows how make the sequence work by inserting explicit memory fence instruction. You can see in the second line is fence. The fences keep the threads from passing the writes. And the titanium architecture. Then we know that the titanium architecture had no legacy software to develop, and thus could afford cutting edge relaxed memory model. The, the model theoretically delivers a high performance when compared to the sequential consistency. By how means it going to give the memory system more freedom of choice. Yeah. We can see in the figure the two threads synchronize. At first, in Italian architecture, first message variable will be zero, and ready is the flag that is used to synchronize among them, threads one for threads two. First, what thread one in first in A, thread one is going to send the message to the thread two. First, it will uh, store the value 42 into the variable message, and then it allows the is ready uh, boolean variable to true. uh, Thread 2 periodically checking the value of is ready. If is ready is not true, it is going to continue. If is ready is true, then it will going to read the message into the message into R2. So in the second one, B one, here it shows the Italian architecture can reorder the reads and writes, in which thread 2 is going to send the message to thread 1. First message will be yeah, like that. But here the solution, but better the solution is to declare the mm, declaration of this ready can be volatile. So we can see in the seat one how volatile is required and how it will allow Itanium architecture to reorder the reads and writes, and shared memory without a lock. Uh, Here the Itanium architecture lacks memory model. Uh, this can be expressed using these idioms. We can see the two idioms here, and the animals, we can see the animals that represents the operations which whose movements is constrained by the animal trainers. We can see they those represents the acquire and release fences. Then we can first we take the first idiom. This is this represents the message passing. Here a sender thread writes some data and then signals the receiver thread that it is ready by modifying the flag location. Mm, we have seen already how it is going to modify, and the modification might be a write or some other operations. As long as the sender performs a release operation after writing the data, and the receiver performs an acquire operation before reading the data, the desired ordering will be maintained. Typically, these conditions are guaranteed by declaring the flag as volatile. I have explained the use of the volatile in reordering purpose. And then second idiom is this is memory cage. A memory cage starts with an acquire fence and ends in a release fence. These fence keep any memory operations inside the cage from escaping. However, be aware that memory cages keep things inside from getting out, and not vice versa. That is the main thing here. It is possible for disjoint cages to become overlapped by instruction reordering, because an acquire that begins a cage can float backwards over the release that ends the previous cage. Yeah, yeah. Thank you.